lecture. We have been discussing the chemistry of hydrides of boron, and so far we have looked at the structure, bonding, as well as the reactivity of these boron molecules. We will now discuss about a few derivatives of these boron molecules. That is, we will discuss about carboranes, where apart from boron and hydrogen, carbon atoms are also present, and these carbon atoms essentially occupy the vertexes in the polyhedral structure of these boron molecules in carboranes, as well as we have metallacarbonares, where apart from carbon and boron centers, metal atoms are also part of the polyhedral skeleton, and that is why we call them as metallacarbonares and metallaboranes, which are where the carbon atoms are absent, but only metal centers and boron centers are form the polyhedral skeletal structure in these type of compounds. So carboranes, metallacarbonares, and metallaboranes, and we will primarily focus on deducing the structure of these molecules by using the electron counting method formulated by Wade, or known as the Wade's rule. So let us begin with how one can prepare these carborane molecules, and we will see one example of preparation of carborane molecule. But before that, what we should know here is that carbon atom has one electron more than the boron atom, because the number of valence electron in carbon is equal to 4, while the number of valence electron is in boron is equal to 3. So that is why we can say that this CH fragment is isoelectronic with BH negative. A fragment, corresponding BH fragment with one extra electron as a negative charge here, will be isoelectronic with the CH fragment, or we can also have the BH2 fragment, which has one additional hydrogen atom with an additional electron, which carries an additional electron, so that the BH2 group is also isoelectronic with CH. So in principle, it is possible to replace some of the boron centers in boron molecules by using carbon atoms or CH fragments or CR fragments. R can be any alkyl, aryl, or acyl group, say, and still retain the structure, because if we add a positive charge to the boron center for each boron atom that we replaced by carbon atom. So this tells us that if we take B10H10 2 negative, which is a closure boron, we know, with 26 skeletal electron pairs, and it has dodecahedral structure. So now if we replaced, this is B12H12 2 negative, B12H12 2 negative only has 26 skeletal electron pairs and 26 skeletal electrons and 13 skeletal electron pairs, and has a dodecahedral structure. And this, if we now replace two of the boron centers in B12H12 2 negative by two carbon centers and obtain a carborane, and if we add two positive charges, because we have replaced two boron centers by two carbon centers which carries two extra electrons, and that is why we need to add two positive charges, so that the charge on the carborane now, instead of becoming -2, it will become 0. And in that case, the structure of these two molecules are going to be, or these two molecules are isoelectronic now, we know, and the structure of these two molecules are also going to be same, because the number of atoms which occupy the vertex in both of these two molecules are also equal. That is, in this case, two carbon atoms tend boron centers, so 12 atoms which can occupy the vertex, and here we have 12 boron centers. So this is how we can relate the carborane molecules with the corresponding boranes, or we can we can think about preparation of different carborane molecules, or starting from boranes. So let us now see how one example of preparation of carborane. So let's start with a nidoborane B10H14 and do reaction in a donor solvent, that is a diethyl sulfide, which acts as a Lewis base. That is why we call it a donor solvent here. And this is now going to form an intermediate with B10H14, where this diethyl sulfide will replace two of the hydrogen atoms in the nidoborane. These hydrogen atoms are the bridge hydrogen atoms, which are acidic in nature, and that is why they can be easily released, and they will be released as dihydrogen here in this way. So this reaction intermediate essentially is reactive here as compared to the parent borane to react with acetylene. So R here can be either hydrogen or alkyl groups or aryl groups or acyl groups, and in all of the cases what we will have is formation of a carborane in this way, B10H10, and the diethyl sulfide will be released, and two hydrogen atoms will also from this intermediate again we will lose two hydrogen atoms as dihydrogen. So the formula of the carborane is essentially R2C2B10H10. So let us now do electron counting for this carborane molecule and then try to deduce the structure of this carborane. So we have, this is the formula of the compound, so let's do a valence electron count. Two R groups are there, and these two R groups are attached to the carbon centers because we started with the acetylene over here, and now each of these R group essentially provide one valence electron to the total valence electron count here, and that is going to be equal to 2 valence electron. So 2 carbon centers will give us 8 valence electron, 10 boron centers will give us 30 valence electron, and 10 hydrogen atom will give us 10 valence electron. So total valence electron is going to be equal to 50 valence electron over here, and now we will have to deduct the electrons which are used for formation of terminal 2-center 2 electron bonds, so that we get the electrons which are used for formation of this skeleton, polyhedral skeleton of this carborane molecule. So there are 2 CR bonds here, and these bonds, so total 4 electrons from these 2 CR bonds, and 10 BH bonds, so 20 electrons for these 10 BH terminal bonds, 2-center 2 electron terminal bonds these are. And now if we deduct these 24 electrons from the total valence electron count, which is going to be equal to 26 electrons, so these are the skeletal electrons which are going to form the polyhedral skeleton in this carborane molecule, so which again is equal to 13 skeletal electron pair. Now again we have learned that as per Wade's rule, for formation of a polyhedron with n vertex, we need n plus 1 skeletal electron pairs. Since here we have 13 skeletal electron pair, so the number of vertex as per Wade's rule is equal to 12. So we have a dodecahedral structure here. Now let us see how many atoms are present in this carborane molecule which can occupy these vertexes. So there are 2 carbon centers and 10 boron centers which can occupy the vertex. So number of vertex atoms is equal to 12. So each of these 12 vertex in the dodecahedral structure are occupied by an atom, either carbon atom or boron center, and that is why what we have is a closed dodecahedral cage-like structure here, and this carborane can be classified as closoborane, and we can see again that the structure of this carborane molecule is identical to the structure of B12H12 2 negative. So we can also draw the structure of this carborane molecule here. So that is the basic structure here, and the carbon centers, because the origin of these carbon centers are from acetylene. So when we prepare this carborane molecule, the carbon centers are going to be adjacent to each other in this way, and the R groups are attached terminally in this fashion, and all other vertex are occupied by the 10 boron centers that we have in this molecule. So these are all boron centers we see, and to each of these boron centers a terminal BH linkage is there. So we should draw these terminal BH linkages. So now in this dodecahedral structure, the two carbon centers we see are occupying adjacent positions in this way, and this is position, if we assign this to be position 1, then this is going to be position 2, and this particular compound we can tell it to be the 1,2 isomer of this carborane here. So that is, we can write as 1,2 R2C2B10H10. Now if we heat it, what is going to happen is that the reorganization is going to happen, and this carbon center is going to change position, and it can occupy one of these structure here or position over here over here. So then it is going to be 1,7 isomer. Once this carbon center comes to this position over here, it will be 1,7 isomer, and then again on further heating above 450 degrees Celsius, this carbon center can move to this particular position over here, which is position 12. So we will have 1,12 isomer as well. So this sort of isomerization reaction takes place when we heat the carborane molecules, as the carbon centers can change position with respect to each other, and that is how we can have different isomers. So now let us see how we can use a carborane and then obtain a metallacarborane. So we will use C2 B10H12, which has similar structure to the carborane that we have, for which we have already deduced the structure. In this case, instead of R groups, 2 hydrogen atoms are attached to the carbon center, but the structures are going to be identical, because only difference is going to be that instead of the R groups, there is going to be terminal CH bonds in this case. But the number of electrons, if you count, you will find again to be equal to 26 skeletal electron pair and 13 skeletal electron pair, and the structure is dodecahedral. Now if you take this carborane molecule and then treat it with a strong base like methoxide in methanolic medium, then it is able to take out one of the boron centers. The base is able to split out one of the boron centers from this carbon molecule, so that we end up with C2B9H12 negative. And the boron center essentially from trimethoxyborane in this way, and so we have to write a 2 over here, and there are 2 additional hydrogen atoms now. These hydrogens will be released as dihydrogen in this reaction. So now this particular species, it's a conjugate base of a Bronsted acid, that is C2B9H12 if we take, and then treat it with an acid, we will have, sorry, this is negative charges here. So C2B9H13, which is a Bronsted acid, and this species is a conjugate base of this particular Bronsted acid, and it is a pretty strong base as such. But if we treat it with a stronger base, that is, if you take C2B9H12 negative and then treat it with sodium hydride, then we will end up with C2B9H11, so that it is able to abstract one of the hydrogen atom from this particular species, and we will have 2 negative charge overall on this particular the resulting compound over here, and also a release of hydrogen gas again here. And now let us do electron counting for this particular species here. So if we do electron counting for this particular species here, so we have 2 carbons, so that is 8 valence electron. We have 9 boron, so that is 27 valence electron. We have 11 hydrogens, so 11 valence electron. We have 2 negative charges, so that is 2 valence electron. So total electron counting, 8 plus 27, 35 plus 11, that is 46 plus 2, it is 48 valence electron. So let us now deduct the electrons used for terminal 2-center 2 electron bonding. So we have to take 2 CH bonds. So it is 4 electron, and then 9 BH bonds. So that is 18 electrons. So total 22 electrons are used for 2-center 2 electron terminal bonds, CH as well as BH. So out from 48 valence electron, if we deduct these 22 electrons, then we will end up with 26 skeletal electrons. So 26 electrons are essentially going to be used for formation of the skeleton in this particular species, and this is going to be 13 skeletal electron pair, and once again the number of vertex is going to be equal to 12, but the number of atoms, vertex atoms, two carbon atom and 9 boron center, so it is 11. So what we have is that though we have a dodecahedral structure with 12 vertex here, only 11 of the vertex are occupied, while one of the vertex is left empty here. So we have a nido structure. So let us try to draw the structure of this particular species here. So we have what we have is nido structure. The structure is based on dodecahedron. So we draw all the vertex of the dodecahedron except for the top vertex over here, which will leave empty. And this is the structure that we have, and let us place 2 carbon centers here, and boron, 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 this is boron, 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 and boron over here. And then also let us put hydrogen atoms, terminal BH bonds. In this fashion. Now, on all of uh, these atoms on this open face over here, there are lobes present in this fashion, pointing towards the apex or vertex, the 12 vertex, which is over here, but there is no atom in this particular vertex, and that is why this we have this sort of a shape over here, and the total number of electrons in these lobes that is present on the open face is equal to 6. So there are 6 electrons and 5 lobes in this way, which is facing towards the 12 vertex in this dodecahedral structure or nido structure, where there is the 12 vertex is essentially absent, and that is why we have the lobes only pointing towards this particular vertex. Now, if you look at this, the shape of these lobes and the number of the electrons occupying these lobes over here, and then compare it with the lobes that are present in cyclopentadienyl anion. Cyclopentadienyl, so we can draw it in this way, that is Cp ligand C5H5 negative in this way. Then what we will see, there are p orbitals in this ligand in this fashion, in this way. This negative charge is essentially delocalized, and there are 5 p orbitals which carry total 6 pi electrons in this cyclopentadienyl ligand. Now, the shape of these orbitals as well as the number of electrons occupying these orbitals inside Cp in this Cp ligand are there is striking resemblance of the lobes present in this particular species, and the number of electrons are also same in both of these two. Number of electrons that are occupying these lobes are also same with that is what is present in case of the Cp ligand. So what one can anticipate from here is that we can replace or we can form compounds which are formed by the Cp ligand by using this particular species as well. So we know one of the species which is formed by, or one of the very important compound which is formed by the Cp ligand or cyclopentadienyl ligand is ferrocene molecule, which is FeC5H5 2, and its structure is very interesting. In fact, it has a sandwich-like structure where the two Cp ligands, these aromatic cyclopentadienyl groups, are actually sandwich the iron center in between, and the plane containing these two Cp rings are essentially parallel to each other, and we draw the structure in this fashion where iron center forms. There is linkage of iron center to each of these carbon atoms in these Cp ligands. So it's a very interesting structure that is formed by the Cp ligand, and similar structure can now also be formed by this particular species over here. That is because the shape of the lobes on the open face is similar to the p orbitals that is in Cp ligand, and also the number of electrons occupying these lobes are equal to the number of electrons present in the p orbitals of the Cp ligand. So we can take FeCl2, and then if we take this C2B9H11 to negative, then we can form B9H11 whole to this sort of a species which has structure similar to Cp ligand again, ferrocene molecule again, because what is going to happen is that now the structure so the iron center is going to come over here, and we will have linkage in this way to the all the uh, atoms which were present on the open face of this nido-carborane anion here, and on this side as well we will have similarly we have to draw the structure here. So another unit of this C2B9H11 2 negative is going to be present, and again there is going to be linkage to the iron center in this fashion. So let us first draw this unit over here, and there is going to be also kept in this way. So this is the structure of this compound, that is FeC2B9H11 2 times, which is similar to the structure of ferrocene, and this we could find out by using this electron counting method. So this is how we can also determine the structure of metallacarbonares. Now we will see how we can reduce the structure of metallaboranes, as well as we can reduce the structure of other types of metallic cluster by using the weights rule in the next lecture. And this essentially brings us to the end of this lecture, and what we have learned during this lecture is how we can prepare carboranes as well as metallacarbonares, and how we can do electron counting in these carborane molecules as well as in case of metallacarborane molecules, and then deduce the structure of these molecules by using the electron counting method. So during the next lecture we will learn how we can do electron counting again in case of metallaboranes, as well as in how we can extend this weights rule to other to predict the structure of other types of metallic clusters as such. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.